Hi class, welcome back to Calculus 3. I'm Dr. Scott Adamson, and today we're going to apply the multivariable chain rule to a reasonably real-life situation involving scuba diving. So first, it's going to be really important in this video that you have the notes nearby. In the notes are a couple of graphs, and it's just going to be easier for you to track with what I'm saying if you have those notes and you have those graphs nearby. So please click in YouTube below the video link, or the video screen, you'll see a little blurb about this video and a link to the document. Or on the website, just click the link to the document so you can have it nearby, either on your screen or print it out. All right, let's do it. Here's the story. There was a paper written in 1981 by K.V. Mackenzie, and in it, he modeled the speed of sound traveling through ocean water, and I'm going to focus on ocean water with salinity 35 parts per thousand. And the speed of sound depends on two things. It's a function of two variables, the temperature of the water and the depth of the water. So what I'd like you to imagine is a scuba diver is scuba diving. And as they're engaged in this scuba dive incident, they're going to go down, so depth is going to change. And as they go down, during the length of the dive, as the time elapses during the dive, the temperature of the water changes because the deeper you go, the colder the water gets. And so we're going to think about the speed of sound underwater as a function of those two variables. And Mackenzie was able to model it. So the focus of this video is not where did he come up with the model. The focus of this video is just using that model. Now we can imagine that this could be important for some studies because we have things like whales and dolphins underwater who use sound to locate things, to communicate. And so the speed of sound underwater is something that scientists might be interested in. So two things that we want to be aware of as well. The temperature is going to be a function of time during the dive. So the dive is going to start. When the scuba diver drops into the water, time is 0. And the time is going to go on. And as time goes on, the temperature is going to change. Likewise, as time goes on, the depth at which the scuba diver is diving is going to change. So in the notes, I know you can't see these, but in the notes are two graphs to demonstrate those two quantities, temperature and depth, and those should be at your availability very quickly. All right, so here's the question. C in this function is the speed of sound, and we're going to measure the speed of sound in meters per second. T is the temperature. We're going to measure temperature in degrees Celsius. D is the depth at which the scuba diver is diving in meters. And what I'd like you to do is, suppose the scuba diver is diving according to the graphs you'll see on the handout. What we want to figure out is, at what rate is the speed of sound changing relative to time? That is, we want to find dc dt, the change in the speed of sound relative to changes in time during this dive. Now, C is a function of temperature and depth. Yet I'm asking for the change in C relative to changes in lowercase t time. So you might be wondering, how could you do that? Well, that's what the chain rule is for. The chain rule allows us to compute this derivative by actually computing 4 other derivatives. We can compute the partial derivative of C with respect to capital T temperature. We can find that partial derivative. We can also find the partial derivative of C with respect to capital D depth. We can find dCd capital D. We can, using the temperature function, we can find changes in temperature relative to changes in time. And dt, we can find the changes in depth relative to changes in time. Now, before we get into the details of the computation, I just want you to make sense of the chain rule. Why does this make sense? And the way we're going to make some sense of it is just by tracking the units. Let's start with dc dt. I'm just going to use brackets just to help organize my thinking here. dc dt. C is the speed of sound measured in meters per second relative to changes in time measured in minutes. If you look at the graphs, the time, elapsed time that we were using in this problem is time in minutes. So the final result of dc/dt should come out to be how the speed of sound is changing in meters per second per minute that the scuba diver has been diving. Now, dc/dt, again, changes in c. C is the speed of sound in meters per second. Changes in temperature. The temperature was measured in degrees Celsius. That quantity is getting multiplied by dt/dt. Changes in temperature in degrees Celsius relative to changes in time in minutes. I hope you can already see it. Meters per second per degree Celsius. Degree Celsius per minute. In terms of some unit analysis here, we're getting meters per second per minute. Exactly the result that we want. But this part of the chain rule, this part of computing the overall change in the speed of sound relative to changes in time, is based on how temperature is changing. As the temperature changes, the speed of sound changes. But in addition, as depth changes, the speed of sound changes. We want the total change, the total of dc/dt. So let's keep tracking the units to see if they continue to make sense. dc/dt. C is the speed of sound in meters per second. D was the depth. We were measuring depth in meters. dt/dt. Depth measured in meters. Changes in time measured in minutes. And so yes, again, if we just kind of analyze these units, we have meters per second per minute. So meters per second per minute caused by changes in temperature plus meters per second per minute caused by changes in depth combined to get a total meters per second per minute. So yeah, the chain rule is the tool we'll be able to use to answer this question, to solve this problem. It just requires 4 computations. Let's go do those computations. So we're going to compute all 4 of those derivatives. 2 of them are partial derivatives. 2 of them are just regular single variable derivatives. We're going to compute all 4 of them. Now, in the problem statement, look at your handout again, please. In the problem statement, it says, we're going to look for dc/dt. We're going to determine or compute dc/dt at the moment in time elapsed since the dive. Time is 30 minutes. So 30 minutes into the dive, at what rate is the speed of sound changing? All right, so the 4 derivatives. The first one was the partial derivative of c with respect to t. Remember, c, the speed of sound, was a function of temperature and depth. This is just the partial derivative with respect to temperature. So go back to your function, please, and track along with me so you can see how to compute that partial derivative. It's just the power rule repeatedly. So the first term, the 1449.2, constant. That constant does not influence the rate of change at all. So the rate of change of a constant is 0. The next term, 4.6t. The derivative of 4.6t is just 4.6. The next term was a minus 0.055 t squared. Power rule, 2 comes down front, decrease the power by 1, and that will compute to be 0.11 t, except it was being subtracted. The next term was a 0.00029 t cubed. Power rule, 3 comes out front, decrease the power by 1, and that term will be 0.00087 t squared. And then the last term, the 0.016d. Now remember, with a partial derivative with respect to t, we're holding d constant. So that will also differentiate to just 0. So there we have it. There's our partial derivative with respect to t. Now keep in mind, we're evaluating this derivative particularly at the point in time that t is 30 minutes. So 30 minutes into the dive. Go to the temperature time graph, please. Go 30 minutes into the dive and read the temperature of the water 30 minutes into the dive. Now, we're just eyeballing the graph, but I'm going to claim that 30 minutes into the dive, the temperature of the water, according to that graph, is about 13 degrees Celsius. So, if the temperature is 13 degrees Celsius, we can compute dc dt at the moment in time that t equals 30 minutes. We would say take 4.6 minus 0.11 times t, that 13 degrees, plus 0.00087 times that t squared. And if you run all those numbers, please do, you will get about 3.31703. Now remember, from our unit analysis, the units on this are meters per second per degree Celsius. Meters per second per degree Celsius. All right, keep that in mind. That's the first of the four that we need. The next one that we needed was dt. Now this was just a single variable function. Again, look at the handout, look at the graph. At the 30-minute mark, bring your eyeballs to that point on the graph, please. At 30 minutes into the dive, the temperature of the water is increasing linearly. And so we can determine the derivative, the rate of change, the slope of that segment of that graph. So what I've done, use your notes please so you can track where I'm getting these numbers from, but I picked two convenient points in that segment, right around 30 minutes. Because it's a linear segment, it doesn't really matter which 2 points I pick, the rate of change is constant. So I picked just two convenient points. I picked the point 20, 12. So 20 minutes into the dive, the temperature of the water was 12 degrees. 35 minutes into the dive, the temperature had increased to 13 degrees. The diver was heading back towards the surface, the water was getting warmer. So the slope there, the change in temperature relative to changes in time. Look, the temperature increased by 1 degree. The time increased by 15 minutes. So the slope here, the rate of change here is 1/15, and if you like, a decimal approximation, 1/15 is 0.06, and that 6 repeats forever. And the units here, temperature is measured in degrees Celsius, time is measured in minutes. So at the 30-minute point in the dive, the temperature of the water is increasing by 1/15 of a degree Celsius per minute. There's the second of the four derivatives that we need to compute. All right, we've got two of the four derivatives computed. Let's go get two more. The next one in order was dc dd, that partial derivative. Remember, c, the speed of sound, was a multivariable function of temperature and depth. We're now going to get changes in the speed of sound relative to changes in depth. So go back to that function. I hope you have your handout in front of you. You can track along with me how this derivative works. It's actually really nice because the first term is a constant. The derivative of a constant is 0. The next term and the next term and the next term, the next three terms all are based on temperature. Since we're doing the partial derivative with respect to depth, we're holding temperature constant. So those three terms are constants, their derivatives are 0. The only term that is going to impact dc dd is that last term, 0.016d. And the derivative of 0.016d is just 0.016. Nice linear function. Now in terms of units, c was the speed of sound in meters per second. D was the depth in meters. And so we're saying that at the 30-minute point in the dive, in fact, this is a constant change, 0.016. The speed of sound is increasing by 0.016 meters per second per meter in this dive. All right, finally, dd dt. Now this was just a single variable function. Please look at your handout, look at that graph of depth versus time. Remember, we're at the 30-minute point in the dive. And again, in that segment, the depth was changing linearly. And so we're going to again eyeball a couple of points in that linear segment. Look at your handout, you'll see the segment that I'm focused on. And we're just going to grab 2 points. It doesn't matter which 2 points because it's a linear segment. So I just grabbed 2 convenient points. The 2 convenient points are 22, 20. So 22 minutes into the dive, the depth was 20 meters. 34 minutes into the dive, the depth was 15 meters. So the depth changed. Look, the depth went from 20 to 15 meters. Got less deep. So that's a negative change of 5 meters. The time, the change in time, 22 to 34, that's 12 minutes. It took 12 minutes for the diver to go from a depth of 20 meters to 15 meters. And so 12 minutes is that change in time. So negative 5/12, which if you like a decimal for it, 0.416, and that 6 repeats. And again, in terms of units, depth was measured in meters, time was measured in seconds, and so this was a negative change of 0.416 meters per second. So we've got this computation, we've got this computation. Let's take our 4 computations back to the chain rule and actually answer the final question. All right, let's do it. We've computed now all 4 derivatives at time t equals 30. Let's just plug and chug and actually answer the question. How fast is the speed of sound changing with respect to time in this particular scuba diving situation? dc dt came out to be 3.31703. And keep in mind the units. They're in your handout. I'm not going to keep writing them. We've been very focused on the units throughout. But look at your handout so you can see these were measured in meters per second per degree Celsius. And then dt was that 1/15th. And I'm going to write it as 1/15th because that repeating decimal is just easier to write 1/15th. And then dcdd was that nice constant 0.016. And then dddt was also a repeating decimal, so I'm going to leave it as a fraction of negative 5/12. So unit-wise, remember this is all going to give us the change in speed of sound in meters per second per change in time, minutes in this dive, so meters per second per minute. So we just crunch the numbers. Grab your calculator, throw it in there, and here's what I get. It comes out to be 0.2145, and again, meters per second per minute. So the bottom line is, in this particular scuba diving incident, based on the graphs that you have, based on that formula from that paper, what we can claim is 30 minutes into this dive, the speed of sound was increasing by 0.2145 meters per second for every minute into the dive at the 30-minute point in the dive. Of course, if we change the time, how's the speed of sound changing 2 minutes into the dive? Well, we'd have to recompute all of our rates of change at the 2-minute point. What's the change in the speed of sound 45 minutes into the dive? Well, we have to redo all that again. But what we now know is, for this point, at 30 minutes into the dive, how the speed of sound is changing. What I wanted you to see here is how the chain rule can make sense in a multivariable situation that also has these single variable functions at play as well. We piece them all together to get the desired result.